Welcome back to ECE 320A. I didn't know how many I would have here today after letting you escape on Tuesday. Thank you for returning. Homework number 6 is due today. Homework number 7 is due a week from today. I believe that's the correct date, the 5th of April. The next Thursday is our third exam, and we may squeeze another homework in between 7 and exam number 3. So it may be over that weekend before the exam 3 that it's due. It'll be due on the Tuesday, the 10th is, I think, the plan. Pardon me? Yes. So right now you should have enough material if you would have studied Unit 7. And the reason I say if you would have, I looked at the statistics, and not very many people have actually looked at the material for Unit 7. Maybe 2% of the class. And there's 50 students, so one person has looked at some of that material. You may want to do that, especially after today's lecture. Homework 7 is dealing with convolution. Homework 8, I'm still deciding what I want that to be, but I think it will be finding the sinusoidal steady-state output response without finding the total solution. You can do it directly from the transfer function fairly quickly. And we'll try to see how we can do that graphically from the S-plane, and also once we learn how to sketch Bode plots, we can do it for any frequency you want if you have the Bode plot information. And that will start to make sense, I hope. Once you have that background, then we can start talking about filters to all sorts of extremes, passive filters and active filters. Let's then get started. What I want to do today is talk about impulse response, and we'll do that for a simple first order filter, but you could do that for any system that you have in front of you. Today you had to find a lot of, for homework number 6, maybe you're still doing that, you had to find quite a few transfer functions or transform expressions. And you could then find from that information, if you know what is being called the input and what's being called the output, you could find a transfer function, and you could then inverse Laplace transform that transfer function to actually determine the impulse response between that input and that output. As we've talked about before, there are many different transfer functions for a given system or circuit, meaning you could have a lot of impulse responses associated with one circuit. It just depends on how you define the input and the output for a given transfer function. We will derive the convolution integral based on starting with what we now know, which is transform descriptions between input and output. We'll look at a simple example or one example, and then I will encourage you again and again to look at Unit 7 material. There's a lot of work on convolution there that hopefully will help you work homework number 7. That fourth bulleted item under goals is something new, and that's not a homework 7 item. So hopefully we will get material enough so that we can have these homeworks being due bang, 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 one right after another for exam number 3. Let's get started, and we will do that with somewhat of a review. I will call this a system, although this particular system is a circuit. where we have this particular system, and since I've already labeled the input as capital X of S, I'm already in the S domain, which means that I can now redefine or relabel this circuit, this capacitor, to have a value associated with its impedance. And the impedance of a capacitor is 1 over SC. This now, if we want to find the transfer function, is really very straightforward. You can simply think of this as an impedance Z1 and an impedance C2, and that X of S, if that's messing you up, just replace it with something maybe that you're more familiar with, if that makes you feel better. That's okay also, to call it that generic source, capital X of S. And we want to know, really, what is the voltage dropped across that second impedance, and if we simply do a voltage divider, meaning I'm generalizing the idea of resistors to impedances, and now if you were to just replace the Z's with R's, I think you would go, oh, this is just a 220 problem. Now you've moved up to 320, and you can now replace these R's with generic Z's and work your problem as if they were R's, except now your Z's are functions of S's. They're complex variables, but now you can do your algebra. You can just play with algebra, except your algebra involves these complex expressions or complex variable S. What's the voltage divider expression in this Z formulation? Okay, so now I've got you thinking R's again. It is R2 over R1 if we were R's. In this generic case, or more general case, it's Z2 over Z1 plus Z2. That's the transfer function between the input voltage X and the output voltage Y. And this piece in the square brackets would be our transfer function H of S. If we go back to the system that we had before, the impedance of the capacitor is now what we directly replace Z sub 2 with, and that's 1 over SC. Z1 was just R1. Z2 again is the 1 over SC. And as we've talked about before, we really don't want to be having transfer functions that are ratios of ratios. If we now put everything over a common denominator in the denominator, we have SC in the basement downstairs, and we have SC in the basement upstairs. Those cancel, and we're left with the transfer function that we're more comfortable working with, 1 over SR plus, whoops, and that shouldn't have been a subscript on 1. I don't think I was that specific in my circuit. It was just one resistor, so let's just call it R. And that's now our transfer function, 1 over SRC plus 1, X of S. Now, before I move on, so here's our transfer function. where are our finite poles? And how many poles do I have in this transfer function? What's the power of s? I look for the highest power of s in the denominator of my transfer function, and that's going to tell me the number of poles that I have, whether I have real poles or complex poles. You can only have complex or real poles. There's not a whole lot of variation downstairs. So if you have complex poles, you know where those are at. If you have real poles, you know those are on the real axis in the complex s-plane. In this case, we are looking for those values of s that satisfy this equation or make the denominator vanish. And our pole is then at minus 1 over RC, which, to just give you this visual, here's our s-plane. And now this pole is a distance from the imaginary axis of 1 over RC. Depending on how we select our resistor and our capacitor influences how deep or how far into the complex s-plane we move that pole. If we wanted a low-pass, this is a low-pass filter, this transfer function, and we will see that it will have a magnitude response that looks something like that. That's the magnitude of h in dB. And this particular point that we do these straight line approximations for is the pole location, or the value of the pole. And this is now 1 over RC. This is sort of additional information, but if you see that you wanted a low-pass filter with a low cutoff frequency, you would think, and now view this as your graphic equalizer. You now want the bass emphasized. You now have the bass flat, and maybe you want to roll off in the treble and higher frequencies, the mid-range and treble. And that's what this sloping line beyond 1 over RC is indicating, that we are attenuating the frequencies. Here's our frequency axis. I should label this. That's our frequency axis. And if we wanted a bandwidth of 1 radian per second, we would select our resistor and our capacitor such that 1 over RC was 1. If we wanted a wider low-pass filter, and maybe with a cutoff frequency, that's what that particular break is called, the cutoff frequency. These are just straight line approximations to our actual frequency response behavior. But if we selected 1 over RC to be 10, can you see that that bandwidth would be increased? If we wanted it to be 100, we would make 1 over RC equal to 100, and that would influence the choice of R and C. And now you can design a filter. You can design a low-pass filter with whatever cutoff frequency you want. And what's the order of that low-pass filter? First. And that actually influences the slope of that line. This will now be going down at 20 dB per decade. And what's a decade? I'm giving you some background to advance your thought process, so when we do jump into Bode plots, you're going to be ready to be at least jogging and not crawling, is the idea. What's a decade? 10. You think of a decade in time, it's 10 years. So in this case, a decade is a factor of 10. If you said, oh, I have something happening at 10 radians per second, and I know what's going to happen in the next decade, that means you're looking at the frequencies between 10 and 10 times 10, or 10 and 100. You said, oh, I want to know what's happening in the next 3 decades. Then you go 10, 100, 1,000, 10,000. And now you have this 3-decade span. Yes. And this is so the question was, this is a log-based plot. It's actually a semi-log plot, meaning one of the axes is logarithmic and the other one is standard. It's not logarithmic. So the vertical axis will be in decibels, dB, and that will be linear. And this one will be in the horizontal. The frequency is logarithmic, and that allows us to show much more information in the same space. And we like it because on that semi-log plot, it allows our lines to move in a straight line instead of a sloping, curving line that would happen if we had linear scales on both the horizontal and vertical. Question? Okay, the question is, we found our pole to be minus 1 over RC, and this is sort of the beauty or confusion with working in the frequency space. In reality, what are our frequencies? We know we don't have negative frequencies. And this minus 1 over RC, if we looked at the inverse of this, where am I? Right here. If you now needed to inverse Laplace transform, or here, let me just show you some equivalent ways of writing this. You could write h of s. Suppose I factored out the RC from the denominator. Then I'm going to push that RC up in the numerator. I have a 1 over RC in the numerator, and the constant now my pole is explicitly identified in that factored form. This would be a pole zero form. Now, what I want to do when I'm talking about Bode plots is I want to actually concentrate on particular values of this complex frequency variable s. I'm going to replace s with j omega, meaning I'm going to be worrying about walking under the big top tent. I'm going to be walking on that imaginary axis, the vertical axis. And that omega value is only going to be from 0 to infinity. It's positive. So this now, when it's j omega, I'm looking at omega values being positive. And that's why in the Bode plot, we're plotting frequencies from very, very tiny, because on a logarithmic scale, we never get to 0, do we? We get to 10 to the minus 1, 10 to the minus 2, or 0.01, 10 to the minus 3, 0.001. We just keep going. We keep going and going. We go beyond the North Pole, right? We never run out of space on a semi-log paper. So we never really hit 0. Is that clear? Now I had another question. Maybe it was answered. Or I... Well, what we're doing is we've essentially, so the question was, our linear scale is in dB, but isn't dB sort of a logarithmic scale to begin with? And that's okay, that's fine, yes. But that's why we use the dB scale, is so now we can just look at dB of 0, dB of minus 20, dB of minus 40, etc. So that's okay. That's why we use the dB or decibels, so that we can now, and lucky for you, you don't have to sit through a class where you learn how to plot all of these linear, semi-log, log, or did you? I had to do that when I was your age. So thank your generation for not having to do that. What? Yes, I definitely walked both ways in snow to school. Let's not get started. I did not live in the desert. Where was I? Wow, I kind of got off the beaten path. I'm in the snow now. But this is our transfer function, and now do you have a better feel for just a RC circuit? Now when you see that RC circuit, you might see a pole zero diagram, you might see a Bode plot. Or you might see the RC circuit. I want you to be thinking all three. And the other thing that I want you to be thinking about is if we inverse Laplace transform that capital H of S, which you should be experts on by now, what would the little h of t be? What's the time domain expression for capital H of S? What's the structure? At least give me that. It's an exponential, and you know what's in the exponential, right? E to the minus pole t, and your pole is 1 over RC. I've already accounted for the minus. And the gain on that is just right there. Meaning in the time domain, this is 1 over RC. That's the gain, e to the minus t over RC. And we're going to call that the impulse response, and we'll make that more clear in a few minutes. But that's now the impulse response of this low-pass filter. And, okay, so what is the impulse response? If I went up to that circuit and hit it with an impulse, this is how it would respond in time. That's all you're saying, is you hit it with an impulse, and between that voltage source, if you applied a voltage source that was an impulse, the y of t, the output across that capacitor, the output voltage, would behave in time like that h of t. And this is how we are going to be doing convolution problems in the next few minutes, is we want to have a system's impulse response, and once we have a system's impulse response, I can give you any signal you want, and you can give me the output y of t. It doesn't have to be a decaying exponential. It doesn't have to be a step. It doesn't have to be a sinusoid or a cosine. I can give you anything I want as a function of time, and you can calculate via the convolution integral with the impulse response of that circuit the output response. And that's the beauty of the convolution. But now we know quite a bit about that RC circuit that I gave you a quiz on last time. And I would say maybe half of you. So I didn't do I got a 50% on that quiz. Oh, wow. Was there an inductor? You're asking me to remember a week ago? Actually, this is the circuit. So there was no inductor a week ago that I remember. And so earlier in the lecture, there was an inductor, but on your quiz, it was just this simple first-order low-pass filter with an R and a C. Earlier in that lecture, I did have a circuit with an inductor. And it was then a second-order system because it had two energy storage devices, an inductor and a capacitor. And then you can do more things with a second-order filter. You could have two poles, or you will have two poles, and so obviously you could get fancier with what it's doing in the Bode plot or in the frequency response. Now, suppose, so this is, let me just conclude this, or I'm not really concluding, but let me sort of make a break and say here is a first-order low-pass filter, and you can make that bandwidth of the low-pass filter whatever you want depending on your choice of R and C. Oh, I wanted to make one more point before I moved on. What's the time constant of that filter? The impulse response is this decaying exponential, and you want to know when is that exponent equal to 1. What value of time t causes this exponent to equal 1? That time is your time constant tau. In this case, your time constant tau is RC, and that tells you how fast or slow, depending on the value of RC, your low-pass filter decays at after an impulse. So if you had RC equal to 1, you wouldn't see a response beyond how many seconds? 5 time constants or 5 seconds. If your pole was now at minus 10, if this x was out here not at minus 1 but at minus 10, now we are saying 1 over RC is equal to 10, or RC is equal to 1/10. Now what's your time constant? Your pole is at minus 10. Your time constant is 1 over 10, or 0.1. Now how long do you have to wait? Half a second. And it's a faster system because it has a bandwidth of 10 radians per second versus 1 radians per second. Is that making sense? Now, what we want to do is suppose, and here is the justification for why we call this the impulse response, or that h of t. Suppose the input, which is x of t in the time domain, suppose that input is an impulse function. That is, x of t is delta of t. If x of t, if our input is an impulse, what is the Laplace transform of an impulse? Replace x of t in the definition of the impulse integral, in the Laplace domain integral. You have delta of t, and what's that delta do? It sifts out, right? The function. So now you evaluate this e to the minus st at t equals 0. It's 1. Now, if that's the case, if we've now excited our system with an impulse function, the output, y, by definition, is the product of our transfer function times the input Laplace transform. But we just have shown that in this case, with our input being an impulse in the time domain, the output is just the Laplace transform, or the Laplace transform of the output is just the Laplace transform of the system or its transfer function, h of s. Which says in the time domain then, we have that this is equivalent to the the inverse Laplace transform of h of s for the special input x of t as an impulse function. This is what we were calling h of t, and that is then by definition the impulse response. And what is that? Well, that's just the response of the system to an impulse function. That's all we mean by the impulse response. And what we want to do now is get more comfortable with how these time domain quantities are related. Meaning if somebody gives you an x of t, a time domain function, and says, here's my input signal, apply that to your system and tell me what the output is, y of t. All you have to know then, if this is a linear system, is you now need to know what is my system. Well, you can describe it by its impulse response. And you guys know how to find transfer functions from a circuit after today's lecture, or after today's homework assignment. You can find the h of s. And you should be, by previous homework assignments, be able to inverse Laplace transform that to obtain h of t. Now you have the h of t. Somebody gives you the x of t. Now we want to know what's y of t. How are these time domain quantities, x of t, h of t, related? Or how can we use those to find the output response as a function of time? So how are x of t, h of t, and y of t related in the domain that they are working in, which is the time domain? And this is begging us to derive the time domain relationship between x, h, and y, and that's going to be the convolution integral. We know how these are related in the s domain, or the frequency domain. We know that y of s, the output, is the product of the transfer function h with the Laplace transformed input x, and those are all capital. Capital Y is equal to capital H times capital X. Let's now just plug that in, or re-express this in terms of the definitions of the Laplace transform. The Laplace transform of y, or to create capital Y of s, that's this integral from 0 to infinity of y of t e to the minus st dt. That's the definition of capital Y of s. Well, we can do the same thing for h and x, but let's now just keep track of the variables of integration. Let's call the first one variable of integration gamma. That's capital H of s. So this is now h of gamma e to the minus s gamma d gamma. And we're into Greek characters, so let's go alpha for the next variable of integration. And that's now x of alpha e to the minus s alpha d alpha. Nothing fancy there. I've simply re-expressed capital Y, capital H, and capital X in terms of the Laplace transform definition. Let's now start pushing or combining some things. On the right-hand side, let's pull all of those integrals to the left. And we have an h of gamma, an x of alpha, and this complex exponential has some shared pieces with it. So let's just combine those two exponentials. And we now have that integral. But what we want to do is we want to actually end up with something on the right that looks like what's on the left. Meaning we want to eventually pull out an e to the minus st dt. And then whatever is left is going to be y of t. That's going to be our time domain expression for y. That's all we're wanting to do. So let's play a little with what's inside. We now have these parts. Let's see if we can make them turn into y of t. Well, one thing that would allow that to be a little easier if we simply replaced gamma plus alpha with t, and then we could see our e to the minus st right away. And this is why you do the calculus, so that you know how to do this. We've now redefined some variables. We're going to let t be this gamma plus alpha. And we can now, if we want to, we can reuse or rewrite alpha in terms of t and gamma, alpha now is t minus gamma. And if we hold gamma fixed, which we will out here, inside we'll let alpha be variable or t be variable. If we hold or holding gamma fixed, then what happens when we take the derivative of this t expression right here? If we differentiate that and gamma is fixed, then the right-hand side doesn't vary with gamma. That was fixed. We're taking d by dt of gamma plus alpha. It's just going to be d alpha. So now whenever we have d alpha, that's the same in this inside piece as d alpha or dt. And now we're ready to start replacing the alphas with expressions of t. Alpha equals 0, the lower limit. If I plug that into the highlighted yellow piece, if I let alpha equal 0 there, t is just gamma. Likewise, if I let alpha be the upper limit, t likewise goes to infinity. And now I can rewrite that right-hand side double integral. I can say I have this integral from gamma equals 0 to infinity. I haven't done anything with the outer integral. But inside, I now have this integral from t equal gamma to t equal infinity. H of gamma, I haven't done anything with gamma, but now I had x of alpha. But what was alpha? That's t minus gamma. I have e to the minus st by the way that I define t. D alpha is just dt, and I have not done anything with gamma. Now what I want to do is actually interchange my integrals, because I really want to integrate in the outside sense with respect to time. And I may be glossing over some of the mathematical subtleties, but I want to make my eventual integral look like this left-hand side, and this left-hand side has a variable of integration of t. So I need my dt on the outside. And I want my e to the minus st out there also. So if I do that, if I now interchange my integrals, I now have this integral from t equal gamma to infinity. And I have this integral from gamma equals 0 to infinity of h of gamma, x of t minus gamma, d gamma. And beyond that, I have this e to the minus st. Since t didn't depend on gamma, I don't have to worry about it being inside that blue bracketed expression. And since gamma is indeed going between 0 and infinity, I can move that to 0. And now I have my outer expression consistent with what the left-hand side was, and I can equate y of t with what's inside that blue bracketed expression. Or y of t is now equal to this integral from t equals 0, or maybe let me how do I want to say this? Let me do the following. I'll just go ahead and use gamma since that's what I was doing before. Gamma equals 0 to infinity of h of gamma x of t minus gamma d gamma. And this is our convolution integral. And that tells us now how x, our input, h, our impulse response of a system, is related to the output expression y of t in the time domain. Meaning if I want to work in the time domain and the time domain exclusively, I can find my output from input and impulse response using this convolution integral. So you need to be able to do the mechanics of this computation. And that's what we will look at in a minute. But before we get there, let's go back and make some observations with what we now know. Here are some observations, and this is what people, when they give you interviews, will maybe start asking you. They'll try to trip you up. Maybe, maybe not. But you will know how to play. You know how to play in the time domain and the frequency domain, and you know how to go back and forth. That's the key. Because sometimes it's more informative to be working in the frequency domain. If you're talking about filtering signals, then you want to be thinking about frequency content of your signal. And that's what the frequency domain allows us. In the frequency domain, and for us in this class, what's nice about the frequency domain is now it allows us to do algebra instead of differential equations. And we like algebra versus differential equations, maybe. It's just that now our algebra involves complex expressions. As a picture, here is one way of viewing it. And this is what you will be playing with in 340 all the time. You'll now just say, oh, here's a system. But based on 320, you know what that system could be. It could be a circuit. It could be a filter. It could be anything you want. As long as it's a linear time invariant system, it has this transfer function, capital H of S. It will produce a transformed output, y of S, given a transformed input expression, x of S. And how are those? So that's the picture in the frequency domain of this relationship between input, system, and output. What's the expression, equation relating y, h, and x? They're just multiplied. That's the beauty of the frequency domain. We can simply multiply things together. This is now just h of s times x of s. And now I knew I would run out of room, so I abbreviated frequency with s. Multiplication in the s domain. Multiplication in the frequency domain. That's how we find the relationship between the input, the system, and the output. Now, let's go into the time domain. Your interviewer is going to give you the following system. And he may be talking, or she might be talking, in the time domain. And they give you this block diagram that structurally looks just like it did up above. But now you know hidden inside this block diagram is a slightly different relationship between the input, the impulse response, and y, because we just derived it. Now you better know, until I'm dead, so that I'm not completely embarrassed by your response. But you better not do this. That's not true, is it? That's one of those circles with a slash through it. That's a no-no. This is not how the input in the time domain and the impulse response function are related. They are not simply multiplied. The block diagram sort of teases you to think that, but that's not what the block diagram means. The block diagram is just a symbol of what you have going on. You're applying an input x to a system that's described by an impulse response h of t, generating or creating an output y of t. And we know how those are combined now in the time domain. Instead of this direct multiplication, which if you want to multiply things together, then you go back and you jump into the frequency domain. And you transform x of t into capital X of s. You transform h of t into capital H of s, and you multiply. That's fine. And then if you want y of t, you simply inverse Laplace transform capital Y of s. So you can start in the time domain, jump over into the frequency domain, do your algebra, and jump back with an inverse transform. And now you're back with y of t. But if you want to work in the time domain, then you replace this incorrect expression with y of t is equal to the integral from 0 to infinity. And a lot of times we use some variable that's not alpha or gamma, something that looks more time related. H of tau, x of t minus tau, d tau. Or, it doesn't matter. You can, and this is where I want to find that one student that watched the video, but this is where we flip and slide. X was, in this expression, x is flipped and slid. What in the world does that mean? Well, what's the independent variable in x of t minus tau? It's the tau. So when we flip something, we flip it around the vertical t equals 0 axis. That's the flip. And the slide is on the t variable, and we slide t all the way from minus infinity all the way up to plus infinity. So that's the flip and slide for x. We need to flip it and slide it through to find the answer. Well, if x is an ugly functional form, maybe h is not so ugly and you would prefer to flip and slide it. That's okay. You can rewrite this convolution integral with x and h basically interchanged. You could say y of t is an integral from 0 to infinity of h of t minus tau, x of tau, d tau. And you'll get the same y of t. It's just one might be easier to compute than the other. Just like if you're doing circuit analysis, maybe mesh analysis is easier for you in this circuit than nodal analysis, or vice versa for a given circuit. And what is this? This is what we call convolution. And what the interviewer might be wanting you to say is multiplication in the frequency domain corresponds to convolution in the time domain. And we are efficient. We're engineers, so we don't necessarily always like to write out that convolution integral. We've created a symbol to symbolize that convolution integral, and this might really confuse you, especially with my ability to sketch. but that's a star. That's a star. So that's not h times x, that's h star x, that's h convolved with x. So if you see that ugly well, it'll be much prettier in your textbook, but if you see this convolution symbol, that means replace the right-hand side with that convolution integral. That's what that means. Questions on that? Yes? X star H? Oh, okay. So now you're going the other way. So now if you find, and typically in signal processing, so the question was, can you sort of interchange the domains and the operations? I'm not sure if that's what you said, but I think that's actually what you were meaning, and I maybe just made it more convoluted. But we have time domain and frequency domain, and this way we said convolution in the time domain corresponds to multiplication in the frequency domain. If somebody now says, oh, I want to multiply in the frequency domain for certain reasons, no. If I want to convolve in the frequency domain, that's now multiplication in the time domain. So if you had a signal in the time domain and you wanted to perform a windowing operation, if you wanted, and this is signal processing, but if you wanted to now just examine that time domain signal between, let's say, 0 seconds and 20 seconds, and you throw everything else away, that's like multiplying that waveform by a rectangular window function. And so now you would be convolving those two signals in the frequency domain to get the response. That may not have meant anything to you. Don't worry about it. You'll get it in a couple of semesters. Okay? But yes, these are dual concepts. Multiplication and convolution, you can now, if you're doing one in one domain, you have to do the other in the other domain. If you switch the domains, you switch the operations. But for this class, convolution in the time domain is multiplication in the frequency domain. Okay? So let's now do an example. And there are many, many more examples in Unit 7. And there are discussions on flipping and sliding, that's important, and intervals and limits. And hopefully I'll try to make those points as we go along. Let's now return to our governing expression. And in general, you might actually be going from minus infinity to infinity with your independent variable, lambda, let's say. So that variable of integration, don't let it throw you. I'm letting it be all sorts of things, alpha, tau, lambda. But it should be h of lambda, x of t minus lambda, d lambda. And let's start with some expressions. Suppose that the input, x of t, is based on when we start our time axis, or where we draw 0 in the sand. Let's now just say that x is going to be a constant 5 from minus 1 to 3. We have a square pulse that somebody's going to begin at minus 1 and end at 3. And we want to apply that to a system. This is the input signal. That's the input waveform x of t. And let's just return to something that we've already talked about. Let's just low-pass filter this pulse. And I'm going to now introduce a particular low-pass filter in the form of its impulse response. And you'll be able to draw this better than I am. But let's let this 1 over RC in this case is equal to 2. So we have a time constant of 1/2. RC is 1/2. So if this tail, if you were drawing this accurately, the tail would be down to 1% or a little less than 1% after 5 of those taus, after 5 time constants. And what did we say our time constant was? 1/2. So in 2.5 seconds, we basically are done with this system's response if we hit it with an impulse. Okay? So if we hit this system with an impulse, we would quit seeing a response after 2.5 seconds, right? But what are we doing? We are hitting it with something at -1. So when do you think this system is going to, and when does this system turn on? It's a causal system, isn't it? It doesn't start until you hit it with the impulse. If somebody said, oh, your h of t is this crazy looking waveform and it begins at -6, that's a non-causal system. Oh, we're not doing causality here, are we? We can. Anyway, that says that if we put an impulse in at 0, we anticipated that and began responding at -6. We're going to deal with causal systems. We put an impulse at time t equals 0 and we get a response. And in this case, our response is basically gone after 2.5 seconds. Now, here's what we are exciting our low-pass filter with: a pulse. Not an impulse, a pulse of amplitude 5, turning on at -1, turning off at 3. If we start exciting our system at -1, when do you think we're going to see a response at the other side of our circuit, at the output? We hit it at -1. What does this impulse response tell us? As soon as we hit it, as soon as we start exciting it with an impulse at t equals 0, we start seeing something, don't we? We start exciting this system right here at -1. We start hitting it. Actually, we just hit it with a constant 5. We hit it at -1. When do you think you're going to see something? In the grand scheme of this time domain here. At not -1. As soon as you start hitting it, the impulse response tells us, as soon as you start hitting this system, I'm going to start reacting. And this is how I react. Theoretically, how long is this tail? Infinite. So now what you can say by just looking at x and h is, oh, I'm going to start seeing a response at -1, and I may have a little residual clear out to infinity. But effectively, how long am I going to be seeing a response? Probably 2.5 seconds beyond when I quit exciting it. So in reality, I'll start seeing an output at -1, and I'll effectively quit seeing it 5 time constants beyond when I quit exciting it. And in this case, my time constant is 1/2. So in 2.5 seconds beyond the point where I quit exciting it, I'm going to quit seeing a response. Everybody getting that image? So we'll see something at -1 all the way, in practical terms, out to 5.5 seconds. Let's now start doing this convolution. Which one do you think I want to flip and slide? It doesn't really matter, but Functionally, the form of this waveform is not very complicated. So if I flip it and slide it, its amplitude's not going to change as a function of its argument. So it's going to stay 5. I'm going to flip and slide x. 1, because I have things on either side of t equals 0, and you can hopefully get a feel for what I'm doing when I flip it. Okay? So I'm going to leave h as it is, except I'm now going to rewrite it as h of lambda so that it's in terms of what the integral looks like up above. And I would encourage you to simply make all of these formal steps as you're doing these convolution problems. H of lambda, so if you want 2 points out of 100, you just resketch h of t as h of lambda. And you would say, oh, that's h of lambda. And I need that to make up part of my convolution integral. Now, I need x of t minus lambda, where lambda is my variable that's being varied. T will actually be slid, so I will adjust that, but I need to make my expression a function of t. Let me just start with x of lambda. What's x of lambda look like? It looks just like x of t, except now your variable is lambda. So there's x of lambda. Now I want to flip that with respect to lambda. I need x of minus lambda. Boy, hopefully you guys are sketching this better than I am. But when I flip, I'm simply rotating about the lambda equals 0 axis, which means that 3 becomes a minus 3. The minus 1 becomes a 1. Does everybody see that? Maybe I do need some shape so that you could see how it's reflecting, but with my sketching ability, that would probably be more challenging than what it's worth. That's the flipped version of x. We want to actually have x of t minus lambda. So t is the variable that we slide. And we will want t to begin way over here at minus infinity, or quite a ways to the left. So let's just sketch it over there. Meaning, if we push this x of minus lambda over to t, if we let t equal minus 10, then we would be way over here at minus 10 minus 3, or minus 13 for the leftmost part. But we're just going to let t be a variable. Correct. We're not going to hit. So the comment was, why are you sliding it so far? Just to make a point. But we can just slide it as far as we need to. Here was t minus, nope, t plus 1, and this was t minus 3. This is 5, and this is x of t minus lambda, and here's lambda. Are we okay with that? All I've done is I've adjusted my endpoints by t. And this is now x of t minus lambda. And if you wanted to check your work, plug in t equals 0 and see if you get x of minus lambda back. If we plug in t equals 0, we get minus 3 for the left side and plus 1 for the right side. We did get x of minus lambda back. Now, what we want to do is figure out the different overlap patterns. And here, so now we've already done the flipping and sliding. Well, we haven't slid. We're going to move t from minus infinity, or as far to the left as we need, up through plus infinity, or as far to the right as we need. Now what we want to do is figure out our overlap intervals and our integration limits. Now we need to look at the overlap patterns that exist. The first pattern is actually the pattern of no overlap. between our two waveforms, x of t minus lambda and h of lambda. And here I mean no overlap of the support intervals. And by support intervals, if I had a waveform, this gets students confused. If I had a waveform that looked like this, what's its support interval? It's non-zero between -5 and +4. That's the interval of support, or its support interval, even though it's negative. It could be negative or positive. It's just where is it non-zero? That's its support interval. Some people think, oh, well, it's overlapping. The two waveforms have to overlap. No, the overlap concerns where they are non-zero. It doesn't matter if they are actually on top of each other when you sketch them. Is that making any sense? So these two, if I had waveforms like this, these two waveforms have an overlap region between +1 and +4. That's where those two overlap. They don't physically lie on top of each other. It's their interval of support overlaps. Is that making sense? And a lot of times I emphasize that by saying, oh, here's this one, and here's this one. Now we're getting back into the elementary grades where we can color and sketch. So now you look at where it's crosshatched, and that's where it's overlapping. Now, in this case, the first overlap pattern is no overlap. Here is our x of t, or h of lambda, and here is, and these may not be drawn to scale, when does this overlap pattern exist? Or this occurs when this particular, as long as that side of x stays to the left of h of lambda. So we need t plus 1 to be less than 0 for this overlap pattern to exist. So this overlap pattern occurs when t plus 1 is less than 0, or as long as t is less than -1, what's the integral of this overlap pattern? 0, because there's no product. If we multiplied x of t minus lambda by h of lambda, there's nothing. It's 0. They don't have any place where they overlap. So this y is 0 as long as t is less than -1. So the first part of your solution is y of t is 0 for t less than -1. And that's consistent with what we argued earlier. We said, when is this going to start shaking, the output? When we start shaking it with the input, which was at -1. Anytime before that, we shouldn't be seeing an output. Now, what's the next overlap pattern? I'll call this a partial overlap. And maybe it's easier to just draw the picture quickly. And now when does this pattern occur? Anything special have to happen with t plus 1? It has to be bigger than 0. And to remain partially overlapped, we also need to combine that or AND that with t minus 3 being less than 0. Or if we just rewrite this, this says that we want t to live between minus 1 and 3. So now once I get t minus 3 to be bigger than 0, I'm going to have complete overlap. And that functional expression, that convolution integral expression, will be different than what this one is. So these are my intervals where this particular convolution expression will be valid. Between t equal minus 1 and 3, what's my convolution integral look like? Y of t. It's going to be an integral of h of lambda, which was 2 e to the minus 2 lambda, times x d lambda. But what are my limits of integration? Minus 1 to 3? So here's the difference. I have intervals and limits. My intervals, where this is valid, is minus 1 to 3. But when is this integral, this overlap picture, when I integrate, I need to start integrating right here. That's where the crosshatches are, up to this variable limit, t plus 1. So I need to go from 0 to t plus 1. And I need to leave that as a variable, t plus 1, because I already have this information in play. I already know this is true as long as t lives between minus 1 and 3. This answer, y of t, might be a function of t. That's okay. Now, we want to evaluate this from 0 to t plus 1. And I'm not going to go through that. I'm just going to write down the answer. That ends up being 5, 1 minus e to the minus 2 t plus 1. And that's true as long as t is between minus 1 and 3. So you replace t with whatever you need it to be between minus 1 and 3, and you'll get your y, your output at that time. From t less than minus 1, it's 0. Now what happens? Now we have one more overlap pattern, which I will call the total overlap. Pictorially, this now I wanted it to be different colored. And this is now, this occurs for what? When is this pattern in play? When is this picture valid? Or when does it happen? As soon as t minus 3 goes through 0, that's when it happens, and it happens for all t thereafter, right? It doesn't change. We don't need to worry about the exponential in this case. That's going to be a function, and we know the functional expression for that. So this occurs when t minus 3 is bigger than or equal to 0. So this says t is bigger than or equal to 3. And what's the convolution integral? Y of t is now, the argument is what it was before. It was 2 e to the minus 2 lambda times 5 d lambda. The only thing that changes is the limits of integration. And these limits are not the same as the interval where it's valid. This integral is valid for all t greater than or equal to 3. But to find the value or expression for y of t, we need to select these limits of integration. And what are those? You go up and you look, where's my crosshatch? T minus 3 to t plus 1. Those are my limits. So now I have the limits from t minus 3 to t plus 1. And you integrate all of that out, and you end up with minus 5 times, well, let me clean it up even more. Let me just say that it's 5 e to the minus 2t e to the 6 minus e to the minus 2, and that's true. And that e to the 6 minus e to the minus 2 is just a number. It's a big number, but it's a number. So you have something e to the minus 2t for t greater than or equal to 3, and that's the infinite tail. We'll pick up maybe with something else probably on Tuesday. Couldn't remember what day it was.